There is a fundamental misunderstanding about what regulation actually looks like when you are building artificial intelligence systems. We often talk about laws as abstract concepts written in parliaments or international treaties. But for the engineers running the training pipelines and inference servers, regulation is simply another set of constraints, much like a memory limit or a latency budget. When Sam Altman calls for a new deal on artificial superintelligence, he is proposing a shift from rigid legislation to adaptive international oversight. Critics argue this is regulatory nihilism, a way to avoid binding constraints. But if you translate that debate into the language of machine learning operations, you see a very different picture. It is not just about politics. It is about how we architect safety into the very fabric of computation. Here is the thing. The core of the New Deal proposal suggests that we need a new international agency to manage existential risks. In engineering terms, this is equivalent to introducing a global hard stop on compute resources. Right now, if you want to train a massive model, you buy access to floating point operations per second, often called flops, and you run the training job. You do not need permission from a central authority to spin up a cluster. The New Deal proposal implies a system where you must verify your compute usage against a global registry before you can access the hardware required for superintelligence. This transforms the regulatory environment from a post-event review into a pre-execution gatekeeper. Now consider the criticism that this is regulatory nihilism. Skeptics say that flexible oversight allows companies to delay safety standards under the guise of innovation. From an engineering perspective, this translates to the difference between a safety interlock and a warning label. A warning label is like the current approach where you might check your system after it is deployed. If something goes wrong, you patch it. An interlock is a physical mechanism that prevents the machine from operating unless specific conditions are met. Critics fear that the New Deal is just a warning label for the entire industry. They worry that without binding legal force, companies will treat safety as a suggestion rather than a hard requirement. This creates a strategic tension where the drive for speed conflicts with the need for verification. This tension directly impacts machine learning operations scalability. Imagine a team trying to deploy a model update across a global infrastructure. In the current system, they can push a new version to their servers in minutes. If a new international agency is required to validate the compute threshold before deployment, that process introduces a significant bottleneck. Every training run, every fine-tuning session, and every inference spike might need to be logged and verified against a central ledger. This adds latency to the development cycle. It means that the time from idea to implementation grows longer. For a startup trying to compete with a giant, that delay can be the difference between survival and failure. The scalability of the system depends on how fast the verification process can run. If the verification is manual or slow, the entire ecosystem of innovation slows down. Furthermore, data sovereignty becomes a massive engineering challenge under these regulatory frameworks. The New Deal implies international cooperation, which often means data cannot cross borders freely. In machine learning, data is the fuel. If you cannot move training data from one jurisdiction to another because of regulatory restrictions, you have to replicate your data storage infrastructure globally. This means hosting your datasets in multiple regions simultaneously to ensure compliance. It fragments your data lake. Instead of one centralized repository where your algorithms can access everything, you have siloed datasets that must be processed locally before being aggregated. This fragmentation increases the cost of storage and reduces the efficiency of your training pipelines. You are trading computational efficiency for regulatory compliance. Latency budgets are another critical area where these policy decisions manifest in code. When we talk about inference latency, we are talking about how long it takes for a model to generate an answer. If the regulatory framework requires every output to be checked against a safety registry before it is shown to a user, that adds processing time. If the registry is hosted in a different country, network latency increases. If the check requires complex cryptographic proofs to verify that the model has not exceeded its compute threshold, the processor has to work harder. Every millisecond added to the latency budget is a trade-off against user experience. In a high-frequency trading application or a real-time translation service, that added delay could render the product useless. The engineering team has to decide if the safety guarantee is worth the performance hit. There is also the question of how we define the threshold for superintelligence. The research suggests some experts look at a horizon of roughly 4 years for these capabilities. Others argue the urgency is overstated. For an engineer, this ambiguity is a nightmare. You cannot build a system that reacts to a future state that is not clearly defined. If the threshold for what constitutes superintelligence changes, your code becomes obsolete. You might build a guardrail that is too strict, preventing useful innovation, or too loose, failing to catch a risk. The lack of a fixed definition means the engineering team must constantly update their validation logic. This creates a moving target for the entire development lifecycle. The debate reveals a growing consensus that the current trajectory of artificial intelligence development may prioritize speed over safety. This is visible in the competitive pressures of the industry. When every company is racing to release the next model, safety checks are often viewed as friction. The New Deal attempts to remove that friction by creating a shared standard. But if the standard is too flexible, it becomes meaningless. If it is too rigid, it stifles progress. The engineering reality is that there is no free lunch. You cannot have maximum speed and maximum safety simultaneously without paying a price. That price is either in the form of reduced performance, increased costs, or delayed releases. So when we look at the arguments for and against the New Deal, we must stop viewing it as a political debate and start viewing it as a system architecture problem. The critics calling for regulatory nihilism are essentially arguing that the industry cannot be trusted to self-regulate without hard constraints. The proponents are arguing that the industry needs flexibility to adapt to a rapidly changing landscape. The engineering solution lies in the balance between these two poles. It requires building systems that are auditable without being brittle. It requires data architectures that respect sovereignty without sacrificing utility. It requires latency budgets that account for verification without killing the user experience. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.